Ben bir mühendisim. Ofiste, evde, yaşamın her alanındayım. Görülmeyen ama hissedilenim. Ben ne kadar görünmez olursam, projelerim o kadar başarıyla tasarlanmış ve uygulanmış demektir. Tıpkı sizi sizden fazla düşünen gizli bir kahraman gibi. Kahramanlık, kağıtla kalem bir araya geldiğinde geleceğe yön verebilecek kadar cesur olmaktır. Çünkü mühendislik, bilim ve doğa alanında tüm bilinenleri yine doğa ve insanlık için kullanmaktır. Tasarımda sadece estetiğin değil, sürdürülebilirlik, enerji verimliliği, çevre duyarlılığı gibi kavramların da altını çizmektir. Mühendislik, modern, konforlu ve doğaya saygı gösteren yenilikçi yaşam alanlarını hayal etmek ve gerçeğe dönüştürmektir. Gelecek kuşaklara yön vermektir. Binlerce yıl önce bir kıvılcımla yaratılan aydınlığı bugün tek bir tuşla milyonlarca insanın yaşadığı yerlere taşımaktır. Geceyi gündüze, soğuğu sıcağa, sıcağı soğuğa çevirebilmektir. İnsanlığın ihtiyaçlarını karşılamak için hayallerimizi gerçekleştirirken yanımızda TTMD vardı. 1992 yılında kurulduğundan bu yana çatısı altında güven bulduğumuz, etik değerlerin teşkili ve temel sorunların çözümü için birlikte çalıştığımız yol arkadaşımız. Farklı disiplinlerden gelen profesyonellerin ortak amaçlar için toplandığı TTMD, üyeler arasında iletişim ve tartışma ortamı yaratıyor, bilimsel ve teknolojik yayınlar yapıyor, üniversite, sanayi, işbirliğine destek veriyor, çevreci ve enerji verimli çözümlerin yaygınlaşmasını destekliyor, yurt dışındaki gelişmeleri izliyor ve sektörü yurt dışında temsil ediyor. Bizler tüm insanlığın iyi yaşam arayışına çözüm buluyoruz. Bizler yarınlarımızı şimdiden kuruyor ve daha sürdürülebilir bir dünya için çalışıyoruz. TTMD, 1992'den bugüne yaşam mekanlarında insanlığın konfor ihtiyaçlarını doğaya saygı göstererek sağlamak için var. Mühendislik mesleğini etik değerler doğrultusunda uygulamak için var. Türk Tesisat Mühendisleri Derneği. Gelin geleceği birlikte yaratalım.
Good afternoon. Thank you for attending our webinar on the subject of why Aperture-Based Daylight Modeling and why not Climate-Based Daylight Modeling. IBIPSA Turkey, Technical Committee of Turkish Society of HVAC and Sanitary Engineers, organize monthly webinars, and this month issue is the lighting. I'm Ayşegül Tereci and the moderator of this webinar and a board member of the IBIPSA Turkey. I've been working on buildings energy simulations since 2004. Today we have an important speaker and quite interesting subject on daylight modeling. Professor Dr. John Mardaljevic will give a presentation and answer our question. And so firstly, I would like to introduce him. Professor Mardaljevic is working for the School of Architecture, Building and Civil Engineering at Loughborough University, and he's an associate editor in the Journal of Lighting Research and Technology. He's a building scientist with a background in physics and numerical modeling. In the late 90s, he had remarkable contribution during the development of climate-based daylight modeling. His practice-based research includes some major projects such as the New York Times building and the Hermitage. From 2011 to 2019, he served as the UK principal expert on daylight for the European Committee for Standardization and led some of the changes to the recently published standard. Today, he will introduce us the basis of aperture-based daylight modeling and give an example how it could be applied in the urban setting. And then he will explain its differences from climate-based daylight modeling. During the presentation, you can send your question through the question section on the panel. At the end of the presentation, I try to ask your question to the Professor Mardaljevic. It is also possible to rewatch the webinar on the YouTube page of TTMD. I would like to express that I'm grateful all our sponsors for their contribution to this event, and I'm leaving to screen to Professor Mardaljevic.
Thank you, Ayşegül, for the introduction. Thank you indeed. So I will now switch over to sharing my slides only. Yeah. So how's that? Is that showing the slides?
Yes.
Yeah. Okay, fine. So firstly, thank you to TTMD and İBEPSA Turkey for the invitation, and indeed for all the sponsors of these events. I've chosen a deliberately provocative title. However, do not be alarmed. I was the sort of pioneer of climate-based daylight modeling. There's nothing wrong with climate-based daylight modeling. However, there may be very good reason to consider other forms of daylight modeling. But first, let's have a look at a landmark project using climate-based daylight modeling. So this was the New York Times, which I did back in 2004-05. And you can see the astonishing amount of detail that was in the 3D model that was used for this. So this was even before the term climate-based had been coined. So vast amount of simulation. We looked at the simulated view from multiple viewpoints on multiple floors, and the aim was to balance the provision of daylight with the control needed for the roller blinds there. So most of the building had a fairly clear aspect and open views. So the idea was to through simulation, design a control system which would achieve this balance between control of solar and glare and the provision of daylight. We knew it needed to be automated because if it's manual blinds, the blinds come down and they stay down. There was a post-occupancy study carried out a number of years later after the building had been occupied, and by and large that showed that the occupants felt the building worked well. But does that mean that the values that I was simulating were similar or the same to the luminous environment that was experienced by the people in the building? That we don't actually know. We know from thermal simulation that there's a big difference between simulated performance and real performance. In dynamic thermal simulation, we can look at the energy performance of the real building, we can compare it with the numbers we simulated, and we often see there's a big difference. With light, we actually have no idea what that difference might be, because we don't routinely record measures of luminance or illuminance in buildings. So we carry out simulations to refine designs, to push them in the right direction, but we're never certain about the absolute values unless we have some benchmark numbers to compare with. And in lighting, we almost always don't. Now let's just have a look at the opening of the new European Standard for Daylight, EN 17037, which, as was mentioned, I worked on this. I led the development of the performance part of that. And what's striking is the word opening appears 139 times in the standard. When you spend a lot of time sitting on a standards panel, you also become aware of all the other aspects of that standard. So there was parts of that standard that dealt with daylight and sunlight planning. And this is where I felt there were real problems, because what appeared in the standard was similar to what all the various countries had, same in the UK and all the other ones that I was familiar with. But if we just look at sunlight, the the measures that are used for planning are incredibly idealized. They only look at certain parts. There's too many to look through here. But if we just focus on a couple here, they don't include the size of the window. They can't produce any meaningful aggregate measures for multiple windows, possibly even on different aspects like you might have for an entire dwelling. And another key feature is they were all conceived in a pre-digital age and haven't really changed. So what you see in the final standard is actually a method like this that's essentially in plan and section form as 2D. And it's not really fit for purpose for a 3D world with highly complex geometry in it. So this is, in Britain, we refer to such things as a bit of a dog's breakfast. A dog's breakfast is a sort of mush of things put together, and it serves a purpose, but it's not very elegant. So this is the dog's breakfast number one that we'll encounter here. So this made me think that what we needed was a complete radical reconsideration of how we do sunlight evaluation. So total back to basics. And this resulted with an incredibly simple idea called the sunlight beam index. And this was a measure of the connectedness of an aperture to all of the possibly occurring sun positions for that locale, and for that particular aspect, its orientation, including any possible obstructing surfaces, which could be window frames, it could be balconies, it could be buildings nearby. And it's an area-based measure averaged across the aperture. So if you imagine 1 meter square aperture with the sun normal for 1 hour, just imagine it stationary for 1 hour, normal to the aperture, you would have 1 meter squared hours of cross-section area of sunlight beam that could pass through that aperture. Okay, so think of it as, you know, this time averaged, time integrated cross-section area of beam that can pass through. And we can visualize this a little bit with a simple animation where we look at just the beam part that can pass through. We've got external reveals there around the aperture. And as the beam moves, you get the reduced cross-sectional area from the cosine effect, but also from any shading there might be. So if we look at this now for a 1 meter square aperture set in a thin wall and the same with a 20 centimeter deep reveal, it has to be somewhere in the world. I've just happened to put this in London. And we look at the sunlight beam that could pass through this aperture throughout the whole year. Forget about the sky, there's no sky there, just whatever the sun is above the horizon and in front of the aperture, it has the possibility to illuminate it. And we look at 8 orientations all around the compass. So if we look at that one there, south, we get nearly 2,000 meter squared hours cross-section area sunlight beam that can strike the aperture. When you have a 20 centimeter deep reveal, that goes down by a third to 1,340. And you can see as you change just 45 degrees southeast, southwest, not much change, but then quite dramatic change, another 45 degrees, and then same to northeast, and even a little bit when it's facing north, very early in the morning and very late in the evening. So that's a single bottom line number, which gives you the connection of that aperture to all of the possibly occurring sunlight positions. We've also got the temporal dimension of this. So I'm sure many of you have seen plots like this before, but just in case not, we've taken all of those hours in the year and we've rearranged it so we've got 365 along the x-axis, the days, and we've got the hours along the y-axis. And when the sun is above the horizon and it's in front of the aperture, then you've got the potential for some sunlight beam. And because this is south facing, the highest sunlight beam will when the beam is nearest to normal to the aperture, which will be in winter when the sun is at its lowest. So that's when you get the most aperture, most beam coming through. Okay, so you've got that single number as before, 1,928 meter squared hours, but we can see the temporal dimension as well. If we just change our orientation by 45 degrees, then it starts to shift over to the afternoon because we're now southwest. And if we have any number of shading devices in front, it will modify it. We're actually now in Italy for this part, doesn't matter, small change. Key thing is that any amount of shading of any type, and you can see the single number, but also the temporal dimension of it. And this geometry can be anything in any complexity. Where it gets really powerful and revealing is, let's say you want to look at an entire dwelling. So this was a study that was supported by the Velux Corporation. So for this dwelling, simply predicted the sunlight beam for all of these glazing groups, its entirety, and then simply added all these together. And to make the temporal dimension a little bit easier to digest, aggregated it into monthly AM and PM totals. Okay, so the total for that entire dwelling in this orientation, and again, I think we're in London here, was nearly 18,000 meter squared hours. So that's the total amount of connection of all of those apertures to all of the occurring sun positions. We know we've got 25.5 square meters of glazing. So that normalized value, which is just total sunlight beam divided by the area, gives you an efficiency factor per meter square of all of that glazing and its connectivity to the sun. So we can see, just going by the colors, that dwelling in total, you'll get the highest connectivity in the afternoon in the months of May, June, July. And if you can imagine you were site planning a residential development, so you've got all these different orientations here, we'll show 8 of them again. You can quite dramatically see the effect of building orientation on the connectivity of all of those apertures to all of the possibly occurring sun positions. So for 0, 0, 0, you can see most of those apertures are facing east, so that strong connectivity is in the morning. Very little, it's all blue there, in the afternoon. If we look round to 1, 3, 5, we've got quite a high overall connectivity, but it's very evenly spread across there. 2, 2, 5 orientation, the total isn't the highest, but the individual AM, PM values, you're getting high values in summer in the afternoon, and in terms of overheating risk, those are the worst sorts of conditions. So you've got a schema which very quickly can sort of tell you about the sunlight interaction of any number of apertures aggregated in any which way. And of course, it's easy to subtract out. You could take away the sunroom, say, and have a look. at the effect. So having come up with this idea for the sunlight beam index, I thought, well, let's have something equally simple for the sky. So as I think was mentioned, my background is in physics, and I think physicists always think, what's the simplest way that we can get the information that we need? So this was in many ways much simpler than the sunlight beam index, but it contained a radical idea, surprisingly radical, and that was to use the lumen as a measure of the connectivity of an aperture, because once you use the lumen instead of lux, you can account for the area. So the aperture skylight index is an area measure of the connectedness of an aperture to the sky vault in terms of the luminous flux received by the aperture from a uniform luminance sky dome. Okay, not the CIE overcast sky. We don't want to bias this to any particular sky condition. It's about general connectivity to the sky, which can have any condition. It can be clear, overcast, whatever. The sunlight beam index had a natural normalization. The numbers just came out of this, whereas for the sky, you need to apply some value. And I just thought, well, arbitrarily, I'll just take a sky which delivers 2000 lux on the horizontal. The reason 2000 lux, because that gives 2000 lumens for every square meter. Most windows are vertical, so a vertical window will receive 1000 lux, and so each square meter 1000 lumens. Okay, and you'll see now how simple radical ideas can be. So here we are with the thin wall. It's vertical. It can be anywhere in the world because the sky looks the same anywhere in the world in terms of how much of the sky dome you can see. Okay, so this is vertical. It's thin wall, so that 1 square meter gets 1000 lumens. When you have a reveal depth, as before, 20 centimeters, now it's 690. These numbers relate directly to the daylighting potential of that window, because as was identified by Vitruvius 2000 years ago, the view of the sky is key to indicating the daylight potential for any aperture. Put some overhang, add some more, and there's that number. Now it's more or less halved. So overall across the aperture, you're getting half the light from a uniform sky than when it was a thin wall. So as before, there's the same scenario, but now we'll add a column for the skylight part. So the aperture skylight index is that green column there. Glazing 7A, 7B, 7C, that's the sunroom. So you can see how much of that is the sunroom. So you get total and how much from that. And then I'm also showing 3 sunlight beam index values. So those are 3 orientations, and those are location specific, of course, because of you need that to calculate the sun position. And that again is London. So now this looks fine. We've got the simplest possible measures that give us information about the geometrical connectivity of apertures to the sun and the sky. But hold on, there was more messy complexity, and this is again now another dog's breakfast here. Dog's breakfast number 2, the messy complexity that is view in buildings. This is what is in the European standard. Okay, a nice view to the outside is one where we've got all 3 layers of sky, landscape, which could be buildings, nature, or a mix of those, and a layer of ground. And what you have in the European standard is exactly the same as what was, well, very similar to what was in British Standard 8206, which was before, and very similar to what is in the country standards for all of the EU and many of the CEN countries also. So you've got this view dependency, which people try to account for. Now, the position of that occupant in that room is essentially arbitrary. There is an infinite number of possible positions and an infinite number of possible view directions. And so they become constrained. And then was one of those very rare, for most of us academics, true eureka moment when you made an insight which changed everything. And for me, it was the realization that this measure that I was using for the sky, aperture connectedness, that is actually equal to the view potential of the aperture. I'm using illumination as a proxy, therefore, for what can be seen from that aperture surface. And I'll show this now. Again, so here's our uniform sky producing 2000 lux. So that 1 meter square aperture receives 2000 lumens. It can't see anything else. Yeah, that's what the hemispherical fisheye view from the aperture looks like. So all of its connectedness is view of the sky, that 2000 lumens of connectedness. When this aperture is now facing vertical, it has 1000 lumens connectedness. Where have the other 1000 lumens gone? Well, if we were to make the ground glowing in the same way the sky is, and we get back to our 2000. That's what the view looks like. Half of the view is of the sky, half is of the ground. Every 1 meter square of aperture has 2000 lumens, possible lumens of connectivity to the outside. Here we can only see the sky and the ground, so it's 1000 each, split down the middle. If we place an obstruction somewhere in the scene, it'll block some of the sky, it'll block some of the ground, so we get less than 1000 for each, and then we'll get some measure of lumens for that obstruction. So then we get a single number that tells us about the connectivity of the aperture to the external environment, including an obstruction. So in a simulation, so here I was using radiance in an incredibly pared down, simple fashion, where I was having uniform sky and ground, and then assigning a glow to any localized ground plane, and then making the external objects, the middle layer, glowing also. And then counting, simulating those lumens that arrive at the aperture. So if we look at this just from a single point in the middle of the window first, we add those up and we get our 2000. So this is the lux that we're getting at that one point. If we put a 20 centimeter deep reveal there, that number drops down. Of course, because we're shading around there, but that value at just one point in the middle That's only true at the center. If you move away from the center and start moving towards the edges, you'll start to see something quite different. So now you can see when you're at the bottom of that aperture, the reveal is shading a lot of the view of the ground and also cutting out almost 3/4 due to the two sides of the reveal. And you get the opposite when you move up to the top there, it's shading out the view of the sky. And so again, just like with the sunlight beam index, the simulation is carried out at a grid of sensor points, the same sensor point grids that you have for the sunlight beam index, actually much finer than this. And so you've got a simple procedure which calculates the basic quantities that you need to know, but it will accommodate any complexity of geometry that you can introduce into the simulation. For view, this now really is a radical proposal, because you transform what was a vector quantity with essentially infinite number of possible solutions into a flux quantity. So it means you go from an infinite number of possible solutions for the internal position to a single flux-based one at the aperture based on each of the 3 view layers. And you'll see this best in an example application where I've taken sort of like apartment building, which we're seeing very, very common now in London, quite deep balconies, because as you can see, people are using them as garages to park their bikes and stuff. So I just quickly worked up a simple geometry with balcony overhangs, surround edges both sides, 2 big glass windows, and a depth of 1.5 meters. And put this in a scenario now in London where it's south facing. The south facing is important for the sunlight beam index part. The other parts of the solution, though, will be the same any orientation and any place in the world. And we'll look at this in a series of stages, first looking at the lumen connectivity to the 3 layers. And first, we'll just look at the glass without any balcony. So that's the context is the shading from the balcony and the window frames and the handrail. So no context, no obstruction. So just imagine the glass floating there, and all that it can see is sky and ground. And it's 8.26 meters in total. So you've got 8,260 lumens of connectivity to the sky, the same for the ground, and there's no obstruction there yet. Okay. Next, we put the context in place. So we've got the balcony, we've got the handrail, and we see this reduction in the sky lumens. And we're now losing nearly half of our sky lumens from all that blockage across the aperture. And similarly for the ground as well. Now the number that we lose is greater than the impression given from the fisheye image, because the fisheye image is only from the middle, which shows you the least worst obstruction. As you move across the aperture to the edges, you'll see more and more of the localized obstruction. For the next one, we'll take away the context and just show the obstruction opposite. So now we're getting this reduction in the sky and the ground lumens, and we've got this single number which gives this connectivity, a single measure of the visual impact of that obstruction from those two apertures. And lastly, we put everything together, and we now have these numbers here, which gives us a true area-weighted indication of the view potential to each of those three layers. And for the red layer, of course, the sky, that gives us an idea of the diffuse skylight potential for that space. So that's the skylight part and the layers. Now let's look at the sunlight part. So as before, it looks just like the unobstructed one, only we're now getting nearly 16,000 meters squared hours because we've got 8.26 square meters in total. Same sort of pattern. And now we'll add the balconies and the overhangs and the handrail. We can see the reduction in the high angle sun. It's cutting out a lot of that in midsummer. Then we'll take away the balcony and just look at the effect of the obstruction. And we see it's taking out the low angle sun. Now in summer, that would be shining into the space. Sorry, in winter there. And finally, put everything together. And here we've got this complete temporal description of how the sunlight beam could possibly connect with those windows for that apartment. So this is aperture-based daylight modeling as it appears in publications. There is a missing link, and this really is the sort of the final part of the schema. It's just being reviewed at the moment, but I'll give you a preview of this. So this is the missing link between planning and performance that really brings everything together. Because as I'm sure a number of you have spotted already, the sunlight beam index does something which is fine in terms of geometry, but what really happens when the sun goes right down is that the intensity of the sunlight is reduced. In the sunlight beam index, I'll call it here SBI Classic, if you've got a vertical window, say facing west, the highest sunlight beam will be when the sun is normal to that window, which means when it's more or less on the horizon. What I needed was something that connected with performance, but still preserved the geometrical purity of the method. And that's most important for the reasons I'll conclude with. And again, it was a simple idea, and that was to include the air mass in the SBI evaluation, because the air mass is essentially a geometrical quantity. So air mass 1 if the sun was directly overhead, and air mass about 40 when the sun is at the horizon. Okay, so we're not including the localized effects of turbidity, evaporation, all these things which will be a signal in the weather files and the climate data, at least not yet. But this shows the transformation. So here's SBI Classic, as you saw before. And when you include the air mass, now it takes away those peaks which were due to the low angle sun at the horizon, close to the horizon, giving this large beam. So it's accounting for this diminution, prevailing diminution of sunlight intensity as the sun goes down. And when you see those things side by side together, you can see this big change here. Okay, now, once you've got the air mass accounted for, then I was pretty damn certain the SBI air mass would be directly proportional to the direct normal irradiation totals that you would simulate using weather files. So I set up a simple scenario to just work through a load of different obstructions. So no obstruction, 20 degrees, 40, 60, and then look at 7 orientations. I didn't bother with north because the solution for north would be similar for most of them. There's not much sunlight there. And then looked at lots of different weather files and compared sunlight beam index totals with the annual irradiation totals. So here is one for Minneapolis, St. Paul, which is quite a sunny place. Forget the colors for east, south, and west. It's not important. The key thing is you get this quite very strong linear relationship between air mass sunlight beam index and direct sun irradiation in kilowatt hours per meter squared. You look at somewhere less sunny, is this weather file for Paris, taken at Charles de Gaulle Airport. Again, a little bit more scatter, but still very good relationship. And so the really neat thing here is that everything in the climate, the localized effects of occurrence of sun and local turbidity and cloud and all of those things, they come down to a single number, which is the slope of that line. So it's 0.549, that gradient for Minneapolis, it's 0.257. And for all the different other weather files you look at, you'll get different slopes depending on how sunny the prevailing sun conditions in that locale. So now, what that means is, with your sun SBI evaluation, you can transform with just that single factor the numbers that you get, giving you the prevailing illumination on a window. You could change that to irradiation if you were concerned about the potential for, say, overheating risk. But it also gives you a good value for the direct normal irradiation that you would get, say, on a PV panel. So now this aperture doesn't have to be a window, it can be any planar surface. So look at the whole schema now. This simple geometrical process, calculation, aperture-based daylight modeling, will tell you about the connectivity to the sun, the sky, the view layers. And this is the absolute crux of this. It gives you a result which is absolutely certain. There's no performance gap there because you're dealing almost essentially with geometry. If you have good geometry, you'll get a good result. Now, of course, you still want to find out what the performance is like inside a space, but that's where the uncertainty comes along. Very nearly finished now. So in this schematic, we can imagine, say, the New York Times there on the left. So in a building like that, where you've got almost an over provision really of sunlight and daylight, the performance is governed by the operation of shading systems. But when you're lower down in the urban setting, the performance potential is largely determined by what's allowed by design and planning. Planning is the preserve of surveyors. Surveyors work with geometry. Development costs are astronomical. People can't make decisions about development when there's a high risk due to performance uncertainty. So, say for example, you can't have a decision for whether or not a building should be built facing an existing one if its outcome depended on the daylight inside that space predicted using, say, climate-based daylight modeling, because the result would depend on the color of the walls, and there would be and still largely unknown performance gap. But if we're to achieve the sort of net zero energy buildings, where one of the priorities is that you have localized generation of renewable rather than using renewables from distant places, then you need to bring in somehow performance considerations which are dependent on engineering into the planning process, and performance there in terms of daylight amenity value as well for people in buildings, health and well-being, but also systems like PV panels, overheating. And so these two disciplines have very little overlap. They don't have any space where they can interact. And aperture-based daylight modeling, which really was just a personal research project over a number of years from sitting on this panel, I believe it's created a space for interaction where planning and performance can start to work together. And so thank you very much for listening.
Thank you, Professor Mardaljevic, for this outstanding and remarkable presentation. Now, I try to ask some question. What is your future plan for the next step of this modeling work?
Sorry, what am I? Sorry, can I stop? I just need to. What?
Of course.
Is that stop? Is that okay with the video now? Are you seeing me?
Yes.
You are. Oh, good. Sorry. Yes. What's my next step? My next step is to bang the drum and to try and gain attention for it. I know that in the real world, things don't happen in the way academics imagine. Academics often imagine we get a research grant, we do something, and then the world changes. It doesn't really happen like that. And I think getting involved with professional bodies. So in the UK, our equivalent of TTMD is CIBSE, Chartered Institute of Building Surveying Engineers. We have our professional body for surveying is called RICS, R-I-C-S, which is the Royal Institute of Chartered Surveyors. And so you've got surveyors and those with building performance, and there isn't any overlap yet between them. And I know that there is a desire for them to work more closely together, but they need to have some basis that both of them can agree on. And my hope is that something like Aperture-Based can provide that. I've served as legal witness on rights to light cases, and these methods have to be able to be understood by lawyers and judges, the legal profession, because that's where planning disputes happen. They end up in court. And what's not going to work well in court is when you have a methodology where you get different results depending on different simulation tools. And we know this from compliance. People, when they chase compliance, they'll use performance tool A, doesn't get them there, then they'll use performance tool B. Oh, we got the result we want. And of course, everything's still the same. So you can't have any methodology that will depend on different tools and different algorithms. You need something which can't be game played, which is purely geometry, but still can inform about performance. And that's the exciting part. In fact, I'm more excited about aperture-based modeling than I ever was about climate-based, actually.
Okay.
And there's another irony here. In aperture-based, is much simpler than climate-based, but
Yes.
climate-based happened over 20 years ago. Maybe simple ideas take longer.
Okay, one of question from Ece Kalaycıoğlu. Thank you for this great presentation, and she asked that which simulation programs we could use to take into account the sunlight beam index and aperture-based lighting. Is there any work on this?
I'm glad that person asked that question. At the moment, no. I mean, I'm doing it in radiance, but yeah, just at the coding level. I mean, it's very simple. I mean, somebody must be able to work up a ladybug or honeybee plugin for something like this. You know, there's no secret about the methodology. I mean, it's just I don't share my code because I'm not a software developer, and I don't even comment most of my code. It'd be a nightmare for anybody to look through, and but that's not what people want. They need some end user tool. It's quite straightforward, and you know, I've described it in a number of papers. So I'm sure maybe somebody's already done it, and I don't know yet. Yeah, they may have. In fact, actually, I did hear somebody had worked up a plugin, but it's quite early days, and maybe they don't want to share it yet. But I would encourage people to share these things, and indeed, you know, for software providers to get involved. I mean, they only get interested when they sense a market. I know from colleagues from the standardization panel for the European standard, and a few of those have seen aperture-based, and again are very excited at the possibilities of that. So if the standard was to be revised at some point, then aperture-based would be a contender. Now, if it appeared in the standard as part of, you know, the initial planning, then software developers would very quickly produce, the tools.
And another question from Volkan Doda. Firstly, he thanked you for this great presentation, and he asked that doesn't the use of sky with constant luminosity bias the result of the sky aperture mapping in the same way the result of the classic SPI and the air mass adjusted SPR are different?
I think I mean you mean to add a performance dimension to the uniform sky. I think it would start to get very messy then, because there isn't anything like an air mass correction for a uniform sky that would. Yeah, I think this questioner means to account for things like circumsolar luminance and things. I think the work that needs to be done is to relate climate-based measures to the aperture-based ones. So the idea being that you start to come up with a good idea of what the potential for daylight might be in the space by calibrating the aperture-based measures against climate-based predictions, factoring in the window transmission and things like that. But you know, it's not about providing, you know, high levels of apparent precision like you can get from climate-based. Yeah, it's about providing measures which are informative of performance and which are robust, resilient, and repeatable, so you can use them for planning.
Okay, and my addings actually. Also I have worked for the city scale energy performance work, and it is really hard. Lots of criteria on these things. What kind of it can be with applying this method to make the easier this kind of works, I think. What do you think on this subject?
I'm not sure if I think means something like well, in an ideal world, you know, if when someone's working in, say, Revit or whatever,
Yes.
that Revit knows that this is a transparent aperture. Revit knows that this might be a PV panel or whatever, and some little plugin will just quickly go and find these values and provide information right at the very early stages of massing, so that you can start to determine, you know, potential for things like, you know, is this space going to have good daylight? Does it need solar protection? Do you need to consider maybe even something like electrochromic glazing because of the high sun conductivity during, say, the the cooling period, summer months? So that sort of, you know, I think you can envisage that information appearing very early on in the design process. What I think has happened with a lot of simulation is we've stopped thinking hard about the aperture, and we just do everything from the inside, and then we even let optimization algorithms run away and do all our thinking for us. I think that's a bit dangerous, actually, because the optimization criteria are never perfect. So I think one of the things about Aperture is it will help both engineers and designers to focus their attention on the key parts of the building, because, you know, the transparent apertures are the weak link, both in terms of heat loss and heat gain, but they're a vital human component. You know, if it was just energy saving, we'd have no windows, just super insulated walls and LED lights, and we'd all go crazy. So we need the windows, we need that connection to the outdoors. We also need view, and I know that yeah, in Istanbul, you've got high levels of development, same like, you know, every big city, and there are lots of concern about loss of sunlight, daylight access. And if you recall from those images I showed, but some of them showed these stepped buildings in New York. They're from the 1916 zoning resolution, which said, you know, basically you've got to have a view of the sky from the ground, so up like that. So that meant the buildings had to be set back. And then in 1961, they changed that. And then that allowed all the super tall buildings to start again, much taller than they were beforehand. So we're never going to go back to something like the 1916 zoning that you had in New York, but we need to have some process in place where which we can use in planning to make decisions about performance potential, especially, you know, PV, because that's when you talk about energy, it's more tangible than, say, daylight. Daylight is still seen as more of an amenity thing, even though it's vital for humans. But the PV part, you can start to talk about that. So it's not about stopping development either, but also saying, well, okay, you can build that, but you need to pay me for loss of performance. So you need these mechanisms in the legal process for that.
Okay. All the question is, I think, finished. I check it, and many attenders thank you for this presentation. Yeşim Çelikol, Uçmantan is thank you for this presentation, and also I would like to thanks again Professor Dr. John Mardaljevic for this presentation, and also sponsors of this webinar. And I'm finishing this webinar. Have a nice day and see you in the next webinars.
Yeah, and maybe building simulation when it happens. Yes, hopefully.
Yes.
But yeah, great. Well, a pleasure. Thank you very much for the invitation, and thank you for everybody for listening in.
Okay.
Bye-bye.
Bye.
Doğru hava uzmanı.